Swayam Prabha. Digital India. Educated India.
So welcome back. Last time we were discussing the topic of Eulerian and Lagrangian points of view. So the reason it is important is simply because of the nature of deformation that we are tracking, and the complexities that are inherent in continuum system as opposed to the simple Newtonian system where we were tracking just point masses. So life is much more complicated when you are dealing with an infinite number of points, and that necessitated a slightly more rigorous look at how we do bookkeeping for displacements. What we saw is there are two ways. One is the Lagrangian way, which is the way you are already familiar with in Newtonian mechanics, and the other is the Eulerian way of keeping track of displacements and velocities. There is a big difference between the two, and the reason the difference comes is simply because how we track the velocities, and because of that we now had to look at how to do the derivative of variables that are Eulerian in nature. And what we realized is when we have to do we have to take such a derivative, we have to take the Lagrangian rate of we have to evaluate the Lagrangian rate of change. Then it looks like this expression that we saw last time where we had just left off, and this bracket dot 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 here denotes any variable which we are measuring in that particular format, right. So now here in fluids what we have to do is we always do a Eulerian analysis. So let's say you have there is a river and the river is flowing in this direction. A particular point of mass, let's say which originates here, this point of mass will undergo a very fast displacement and end up at a very different location. So in order, if you were to do the Newtonian mechanics, you would have to, or the Lagrangian point of view of doing things, then you would have to track the motion of this particle and as it goes through. Now imagine yourself sitting maybe in Haridwar next to the river Ganges, and then some mass is flowing by. That mass will flow by very fast, and it will flow down to a very long distance. So in order to understand the velocity, you now have to run after the particle as it moves in the river. That is a very difficult proposition for fluids where the deformations are very large. So there what we do is we cannot do that. So what do we usually do? Well, I mean when you are as I said maybe in Haridwar sitting right to the next to the Ganges, you focus your view onto a small and limited section, right, of the river, and then you just notice the patterns that come through. So we do the same thing, and here what we will do is in fluid mechanics we are used to doing the same thing. We divide this entire thing into small grid points and then say that the velocity here, so there is some velocity that is associated with this. Let me be consistent with the notation. So this is u bar. So this velocity is there. There is some other point. This has some other velocity maybe, and I'm just drawing some vectors at random here. Now we identify this velocity u as the velocity of the mass occupying the grid point at that exact instant. So in the next instant this mass would have moved to some other window, some other mass would have come into this. So this velocity will now be reflective of the velocity of the new mass that has come into this. So it is no longer the Newtonian way of doing things where we are keeping track of velocity of a single particle. Here now the velocity of this grid point fluctuates as new mass comes in and enters and old mass leaves the system. So as mass flux occurs in this box, your velocity keeps on changing, and so this vector u is now representative of something slightly different. So this is my Eulerian point of view, and when we do a derivative of this, we can no longer do a simple time derivative. So this now u is a function of time and location, and I have to take care of my derivative in this particular manner. So so this creates an interesting scenario. For example, let's try to do example 1. Let's say evaluate acceleration for, let's say there is a velocity field which is given to you as k times y square I hat plus k times x square j hat. Now, if you had to calculate this displacement, this acceleration, you have to do what we did earlier. You have to take this Lagrangian derivative, and this now would simply be my right. So, so now we already can see that this term is 0. This velocity is not fluctuating with time. So, you only have contributions from these two terms, and you can very easily identify what these are, right. So, this is, for example, equal to k y square, and this is k x square, and if you had to evaluate this, it would simply be 2x j hat. Similarly, you can do it for the other one. I am not going to complete this. The reason I am trying to I wanted you to look at this example is because, interestingly, we are used to an idea of acceleration when velocity is changing in time. But in this example, there is no change with time. There is only change in the spatial direction, and yet you have an acceleration. This is what changes in the Eulerian view of things. Similarly, if I one more quick example, example 2, let's say. So, let's say my u is nothing but some t square I hat, right. Then you now have, if you had to calculate acceleration in this case, which again just like the before, you just end up with this, right, which is 2t I hat. So, in this case, because I do not have any spatial terms, my acceleration in the Eulerian and the Lagrangian, if whichever derivative I used to take, would have been sort of the same. So, here things are slightly simpler, right. Okay. So, this is a key difference. So, the take home message is there are, because in continuum mechanics the way we look at position and how we do a bookkeeping of what and how. So, what are we doing a bookkeeping of and how we are doing a bookkeeping of. In Newtonian mechanics, you only had to track a point or some simple finite number of points, and then this Lagrangian way of doing things sufficed, and there your velocity now is a function only of time, whereas here it is something, it's quite different, and the reason is now you are doing a bookkeeping of this huge infinite number of points in continuum mechanics. Okay, so this gives us this is an important mathematical preliminary to be doing for the sake of this course, because we will be needing to evaluate these in our experiments. So, it is important to realize how the experiments are being done, and also to make sure that when you are measuring velocities in experimental systems, they are what you intended them to be or what they should be, right. So, that is why we are covering all this. These are again all preliminary requirements for the flow of part of this course. In flow visualization, we will use these equations that we had developed in order to understand what a streamline, streak line and path line is. We will come to that in a few lectures. There is one more mathematical preliminary that I would like to do right now, and that is that concerns correlation and covariance. So it's on it would appear that it's slightly different from what we have been doing, but you will see that in PIV these concepts are very, very important and are very much required for flow quantification. So let us look at covariance and correlation functions. Now, in order to do this, we will introduce the idea of covariance and correlation from the perspective of probability theory. So, in probability theory, we have if you have done a course in that, you would have experienced the concept of a random variable that takes on different values at different instances or different or it can take a range of different values, right. So, so let us say we have a discrete random variable x. So, for a random discrete variable, let us say x, we define something called the probability mass function we will call it, let us say, p of a of x by this equation. So, the probability mass function p bracket a is basically nothing but the probability that your discrete variable x takes the value a. Right. So, this is how my probability mass function is defined, and if once you have something like this, then you can also define an expected value of x is defined as, okay. So, my expected value, often written as e of x, okay, this is defined as a sum of x into px, where x is a value that the variable capital X takes. Okay. So, this capital X is the discrete variable and x is the value that this variable takes. So, this is my expected value. Now, you will recognize this is more or less like doing an average in some sense, right, and we will use this idea of expected value later on for our analysis. I am defining right now everything in the way you might be accustomed to if you have done a course in probability theory, and then we will extend this to time series data or a series data. Okay. And in the case of continuous functions, continuous random variable, I am sorry, continuous random variable, we define something called as the your expectation is now defined in terms of, so it's minus infinity to, so this variable x can take, let us say, any value between minus infinity to plus infinity, and you have x, and then we have an fx, which is also known as the probability density function. Okay. So, the probability density function is a function such that integral of just fx dx is equal to 1. So, the probability of that random variable occurring would be just 1. Similarly, here just the summation of px over all possible values of x, that is going to be 1. So, that the variable is going to occur, is going to take at least one of the values in the given set. So, this is just one particular variable. Now, you can extend this idea to two related variables x and y. So, if you have two related variables, then we are going to define what is known as the joint probability mass function, and from joint probability mass function we are going to define a function called covariance, and we will see how correlation is related to that. So, let us say you have two related random variables which we will call x and y. One can define the joint probability mass function as, let us say, p of x comma y is this should be small. So, in probability theory usually the capital letter is reserved for the variable, and the small letter is reserved for the value it takes. So, here when I am writing it as small x, it basically means that the capital X takes a value of small x. So, this means that this is equal to the probability that x takes the value small x and capital Y takes the value small y. So, this is my probability joint probability mass function. And similarly, you can define the probability density function for x and y. So, for continuous, this is for two related, here I have missed the term discrete. So, this is for discrete case, and similarly you can define a joint probability density function for continuous variables, not A, for continuous variables x and y. I am not writing x and y, it is sort of understood that it is for x and y. Right. So, now we want to define something called covariance, and so then we define the covariance of two random variables capital X and capital Y denoted as cov. So, the function covariance is denoted as the letters COV, and so COV now x comma y is nothing but expectation of x minus expectation of x and y minus expectation of. Okay, so this is the definition, and you will see that I am writing in capitals because this is not yet taken any. This is consistent with what we have defined before, right. So, this is expectation of capital X, and on the right hand side you had the small letter. So, my expectation is in all capitals. So, this you can simplify also. You can now write it as expectation of x y minus y expectation x minus x expectation y, and plus expectation x expectation y. Okay. Now, if you simplify this, now expectation x, that if you take expectation x is already a fixed value. So, if you were going to take expectation of y expectation of x, it is nothing but expectation of y multiplied by expectation of x. So, if you were to simplify this overall thing here, you essentially end up getting this. So, this defines a function called covariance, which is a very, very important function. So, let capital XT represent a series of discrete data. So, basically say XT is nothing but a list of values xn, okay, small value. So, then taking our cue from the previous expressions that we saw, we can define a mean or expected value of capital XT and denote it as so basically my subscript is telling you that it is it's a series data, okay. And you can have two different series if you want, and you can do a covariance of XR, let us say XR and XS, and this you will define it again just using my previous. So, here or sometimes people just use mu, and this is this is okay. So, so now if you have to define something called the auto covariance function, then the word auto implies that you are using the same series data. So, if I had to define now the auto covariance function, which is also called AC VF in short. So, we can now define the auto covariance function as let us say this is some value h, okay, as you are taking now data from the same series. So, this is x t plus h, and let us say this is x t, okay, where h is variable. So, you can vary it from across different values, and you can now define an autocorrelation function and use this same now this gamma h to define an autocorrelation function, which is nothing but a covariance function which is normalized. So, the autocovariance function, which often is written as rho h, is nothing but is defined as my gamma h by gamma 0. Okay. So, basically 0 means my h is equal to 0 here, and here you will vary h again at different values. So, my h is varying so that I can hop from one discrete value to the other, right. So, this is my autocorrelation function, and cross correlation function is nothing but you doing the same thing now with two different series. So, you have some series data here and you have another series data XS. Then if you do the covariance function of two different series, then you will call it a cross correlation. You will not call it, it is just called a covariance, and when you do the correlation it is just called cross correlation, just simple mnemonic to help you remember. Okay. So, now these are two important functions that we are going to use. we now want to understand what is the physical implication of this, right. So, why do not we try to understand with a couple of examples here. So, let us say we want to understand what this really signifies. So, let us say you have a function x, okay, which is nothing but some sine of t. Now, here I was defining it for discrete data. You can define the whole thing again for continuous data also, but I am just going to show you. I am not going to derive or explain everything in too much detail. Sorry, rather I would not do too much extensive calculations. I just want you to understand the physical implication of what this correlation function means. So, let us say you have two discrete sets of data, one coming from sin t and again another one also coming from sin t. So, what do you have? You have nothing but two data sets, both are resulting from the same type of graph, which is a sin t, right. So, this is. So, now what I want to understand is how will my variation in rho look like, rho h as a function of h. This is essentially now become a autocorrelation, right. Now, you see you are going to be multiplying the way things are. You are now going to be multiplying here expectation of x y minus expectation of x minus y. What you will see is in the autocorrelation function, you will get a maximum here when your h as you change it over time. H is the maximum at rho h is maximum when h is equal to 0, which is at 1, and then it decreases, and then finally it keeps on repeating itself. So, it again reaches a value of 1 at a distance of 2 pi and keeps on repeating. So, this function rho h is now my looks like a periodic function just like the original function, but basically at h equal to 0 it is saying that these two functions have the maximum overlap in some sense, or these two are the maximum alike. So, because these are the two same functions, they are obviously going to be the most alike when they are just overlapping each other. So, there is no so that in that sense your autocorrelation here becomes a maximum when h is equal to 0. And you can do this calculation for yourself and see. I am not doing it right here, but if you now change this so that my x is equal to sin t and my y was now coming from sin t plus pi. Okay. So, my x now looks like this, whereas my y is going like that. So, you see here the two are almost in opposition at when they sort of when they if you just took this particular y and moved it upwards, when there is no when the h is 0 or the displacement between the two functions is 0, my rho is now going to be 0 here, and when you move these two by pi, again you will have the maximum overlap between the two. So, these two functions become similar when you translate the one of the functions by pi. So, your rho now reaches your maximum of a value of 1 at pi, and everywhere else it has a lower value, and this keeps on repeating. So, this is again a periodic function. So, my correlation function here essentially tells me that if you have two different waveforms, by what value I can shift them in order to get the maximum overlap. If the two functions are not the same, here I have deliberately taken sine and sine, which is why it is reaching a value of 1. If it were not the same function, it would reach a value lesser than 1 whenever there is a maximum overlap. But basically what this is telling you is by how much can I displace one function so that the match between the two functions is the maximum. So if you did not know these two, functions were not given to you a priori, or you are just given a set of discrete data, you could calculate the autocorrelation function, or the cross correlation function here, and you would be able to tell by what value should you displace one of the functions in order to get a good match. So this is an idea that we will use quite a bit when we do particle image velocimetry, and you will see that we will have unknown displacements that we will try to back calculate by moving one image over the other, displacing it by various amounts, and seeing when the cross correlation function becomes a maximum. Okay, and that way we will be able to get very accurate measurements of unknown displacements. So this is another mathematical preliminary that you might want to go into by yourself and acquaint yourself with, because we are going to use these ideas. Right. So we will stop here today, and we will take up a slightly new topic in the next class. Okay, thank you.